Alright, so what we're starting with now is the lens cases. So the cases are basically about where the object is placed, how the image would be formed, and all of that stuff. So let's begin. So the first case is of an object which is placed at infinity. Now this, for example, could be the sun, some star very, very far away from us. How would its image be formed using a converging lens? Now the idea that we need to remember, and this is like a slightly different case than the other ones, is that the rays from an object which is so far away, the rays appear to be parallel. This is also something which is really important for your ATPs, because a lot of the times the examiner will ask you for a experiment to find the focal length of a lens. Case 1 that we're just about to do is what you would use then. And the idea regarding the parallel rays is simply this. This is where we ended last time. So let's say that there's an object like this, and we are looking at this object from somewhere here, right? So this is the observer. This is how we're looking at this object. So if we look at the rays from this object, it would probably be something like this. So if I make it from the center, then like this, and then like this. But if I take the same object and move it further away from the eye, now let's have a look at this. So now the rays have moved away much further, and the rays appear to be, I can say at least, more parallel, right? So if I keep increasing this distance away, the rays become more and more parallel. So theoretically speaking, for an object at infinity, the rays appear to be parallel. Again, if you remember the steps of making the ray diagram, then you know that the first thing that you do is, given the focal length, you mark the f and 2f points according to the scale given. You will be given the scale like this, where the value of these boxes would be given to you. Here it's very, very straightforward that this one large box is 1 centimeter horizontally and vertically. And also, because this is the first case, I wanted to keep this easy, so it's already been done for you. So if you look at this from here, so 1, 2, 3, 4, 5, this is f, 1, 2, 3, 4, 5, this is 2f, and the same thing on the other side as well. All right, so let's say, just for aesthetic purposes, I do have the sun here. So let's say this is rays from the sun coming in. All right, so the rays that I would draw would be like this, that first off I would make ray 1. So a ray that goes like this. And just because I want to recreate parallel rays here, this is one of those only cases where, against my own will, I will not be using rule number 2. Instead, I'll be using rule number 3, because that's the one which can create a parallel ray to this. So I'll just pick this ray up. I'll just copy paste it here in this way, right? So this is that ray. I'll bring it back towards the center like this. Now I'll just zoom in to see if everything's to scale. Again, as would be the case with you drawing it in your exams, I've made a slight, not really a mistake, but I should have done better, to use a pencil as sharp as possible to make sure that your values are also as accurate as possible. So this is ray 3, rule 3, which is that this ray which is perpendicular, which is first passing through f, after refraction, it's going to become parallel to the principal axis like this. And as you can see, it's forming at a very, very sweet spot. This will always be true, which is f. So in this case, the image is formed exactly at f. This is the image. All right. So here you have this gap. So here you should write that the image is formed at f. And this is basically that image of the sun that we would get. All right, now properties. So for each of these lens cases, we'll be going through the properties of the image formed, and they will usually be in this same idea. So first of all, the question that I would ask is this image upright or inverted? So for example, if I just ask you to imagine this arrow here, which was here, so the image is upside down, I would say this is inverted as opposed to upright. This is inverted. Next, another question that will be asked is this image real or virtual? You've already encountered this when talking about the images formed by plane mirrors, which were virtual. If you remember how the ray diagram of that looked like, that's because we took the ray behind the mirror as dotted lines. Those broken lines represent virtual rays. Here these are solid lines, so the image formed is also real as opposed to virtual. Third, now this is something you will also have to discuss each and every time. Is this image larger than, smaller than, or the same size as the object? Now obviously if we are capturing this on a screen, on some piece of paper, this is really a fraction of the original object. So I would say this is a diminished image. And if I think about the magnification values here, magnification is image height over object height, because this is much less as compared to the object height. If we just think about the fractions and the values it could have, it's going to be a value which is less than 1. All right. So these are some common properties that we'll be writing. So inverted versus upright, real versus virtual, and then diminished or magnified or the same size. That's what will differ in each of the cases. So the application of this particular case is in telescopes. So we use lenses like this as well. Not to mention in this case of the ATP, where we would be asked to find the focal length of the lens. Case 1 done. Let's go on to case 2. So what we'll be gradually doing in each of these cases is we are bringing our image, our object, closer to the lens. First it was at infinity, now I brought this in such a way that it's just beyond 2f. So focal length is 5 centimeters, so the same thing as before, it's again been marked. In the next cases you will have to mark this, and the object is also placed. All right. Again, you just have to make the rays. Scale is also relatively straightforward, and again, because everything's already been done, you don't need to do much here. So the first ray that you would make is this. Again, now I'll remember to use the thin ink such that it's going through the optical center. This is pretty nice. Could probably be slightly better. So like this. This is ray number 1, then ray number 2. So this ray parallel to the principal axis, it's going to get refracted through F. So through F means like this and this. All right. So this is how your ray diagram is completed. Again, where the rays intersect is your image. So this right here is the formation of the image. So what you need to remember is where the object is placed, where the image is then formed. So if the object was placed beyond 2f, the image formed is between f and 2f. So that's what you would write here. So the image is formed between f and 2f. Next, again, properties and applications. So properties, first, is this upright or inverted? It's still inverted, because if you look at the object, the arrowhead was at the top, but now it's at the bottom of the image, right? Next, is this image Real or virtual, because it's again still solid rays. The rays are actually coming from the object. So this is a real image. Regarding magnification, again I would say that this is still a diminished image. And I can see that very obviously here if I zoom out again, because the image is smaller than the object. You see the same thing with the distances, you see the same thing with the heights. All right. Now, applications of this. So this is used in the pinhole camera. Now the examiner does ask sometimes how it's used in the pinhole camera. Also talk about that in a while. So with pinhole cameras, the idea is that there's basically a box with a hole in the middle, and you can add a lens here for greater accuracy. And what we do is we adjust the distance of the object from the lens until we get a sharp focused image, which is formed on the film, right? So that's a real image. All right. Apart from this, this idea is also used in projectors. All right. So with projectors also the same thing happens. Actually, my bad. It's not projectors here. Projectors come later in another case. Another application of this case too is in the human eye. So for example, if you look at something right now in your room which is further away from you, and if you try to basically place it between your fingers close to your eye, right? It looks that small. But when you actually go close to it, it's not actually that small. So the human eye also forms a diminished image. It's a real image that forms on our retina. We do not see it as inverted because a brain being a processor in itself, it flips the image back again. Case 3. Object at 2f, focal length is 6 centimeters. The scale is given, so this time we'll have to mark everything here. Object of height 5 centimeters is placed 12 centimeters from the lens, and we have to show the formation of the image. All right, so this time we have to do everything from scratch. Let's start. So first of all, given the focal length, let's mark the f and 2f points. So from here, it's going to be 1, 2, 3, 4, 5, 6. This is F. Let's mark this. So this is F. Right, let's double check. 1, 2, 3, 4, 5, 6. And then 2F. So 1, 2, 3, 4, 5, 6. So here, this is the 2F point. And again, I'll just need to mark the same points on the other side. So let me just copy this. All right. So this is so we mark the F and 2F points like this. So F, 2F here, right? So 1, 2, 3, 4, 5, 6, and then the same way 1, 2, 3, 4, 5, and 6. All right. Object of 5 centimeters placed 12 centimeters from the lens. So if the focal length is 6, and if it's placed 12 centimeters, this means it's placed here, right at 2F, and the height is 5 centimeters. So it must be 5 boxes high. So 1, 2, 3, 4, 5. All right. So that's how the image is. Let's zoom out to see if everything looks symmetrical. It does, so we're doing this correctly. And now we start making the rays. Again, same thing. So rays through O are undeviated. Using the thin ink for this again. Looks pretty neat. And then, according to my preference, I'm using ray 2. So ray 2 is like this. and then it's going to pass through F. So with the ray passing through F, what I can see is my image forms exactly at 2F. So this is a very symmetrical case. All right, because the object was at 2F, the image is also at 2F. So this is a case of symmetry. And when you look at all the cases, once again, you'll see exactly how this works. This was the object, this is our image. All right. Again, image formed. So when the object was at 2F, the image is also formed at 2F. Properties. So first of all, now it's becoming a habit. This is an inverted image. This is also a real image. And because the distances are the same, by similarity, we know that their heights would also be the same, which you can also count. For example, this is also 1, 2, 3, 4, 5 boxes. This was also 5 boxes. So there is no magnification here. This is same size. If somebody asks me for the magnification value, I just say that because the image height and the object height are the same, this is equal to 1. All right. Applications. So where is this case used, where we have the object placed exactly at 2F, is it's used in a photocopier machine where it needs to basically it's fed an image, a digital image, and it needs to produce it's fed a digital image. And again, by image, I just mean that data, and it needs to recreate something of the same size. So that's where we use this lens.